Hello everybody, my name is Professor Soborno from Very Science Lab. Welcome to continuity in two-sided units. Alright, so what are we looking at today? Well, let's say that we have a graph. So now, this background isn't very handy for a graph. So instead, I chose to have this one. Alright, so now, let's see what we can do with this grid. Let's say I did 5, 10, and then 10 on the other side. And alright, so that's the horizontal part complete. And now for the vertical part. So 5 and 10. That's the vertical part complete. Now time for the horizontal. Oh goodness, we're already finished. So now you can just think of each of these marks being 1 unit. So I'll just mark the first few to make sure you don't get confused. And 1, 2. Alright, so now this is our graph. And let's say right here we have a function f of x, and this isn't any normal function. It has 2 different faces. And so, if you took a 2-faced man, then first thing you do, take out his eye. Oh, whoops, that wasn't included in this procedure. But second thing you do is you take one face, you put it away, I guess. So you take one face and you split it from the other face. And voila, now you have brackets. Oh goodness. So now, let's take the first one. So f of x will be x squared minus 1, let's say, when x is less than or equal to 1, negative 1, and when x is greater than negative 1, our function will be in the likeness of x plus 2. So that means that if we say it would probably be helpful to draw more of these. But the thing to explain here is that if from this point, from negative 1 to the right east, this would all be, I should probably highlight this instead. So this whole thing to the east, that is all x squared minus 1, while this whole thing to the west is x plus 2. Now, let's label these things, I guess. Minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, minus 10, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, and minus 10. Alright, and final stretch, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that's it. Alright, so now this is how we're going to draw it. So we take x squared minus 1, which we'll say for now is this light green part of the function, and we'll graph it. So if we take x plus 2, if f of x is x plus 2, when x is minus 1, this is the thing you need to understand. That means that, I got it messed up. Switched up the symbols. So, if we say that f of x is equal to x plus 2 when x is less than negative 1, then for -1 and beyond. So that means that we can say xy over here, -1, -2, -3, -4, -5, -6, and so on, and so on, and so on, and look at that, we're done. So now, what would y be? Well, -1 plus 2 is going to be 1. -2 plus 2 is 0, and I think you can see where this is going. -5, -6, -7, -8. Alright, now we can graph this. So, just like in classic 8th grade stuff, you can take and plot all of the points. -1, 1, -2, 0, -3 over here, -4 over here, -5 over here. And let's be honest, this is pretty boring. And that's it. Alright, now let's zoom out from here. And here is our beautiful thing. Now you might think the next point is logically over here, but wrong, wrong, wrong. Because what's actually really happening is that we're stopping this part of the function in -1, and we're starting this red section, which is actually going to be x squared minus 1. So now we can draw this, but it stops over there. It completely just stops. And now there's kind of like a blank point. So x squared minus 1, how do we draw that? Well, we're going to plot the points in orange and draw the graph in orange. So f of x is x squared minus 1 when x is greater than 1. Should have probably done this prior. So now we can take a new table, and I guess we could go all the way up to 10. So no, we really only have room for 4, I'd say. So now for x and y, 1. Now 1 squared, oh, I forgot 0. So let's just put that in a tiny thing over here. So 0 squared minus 1, 0 squared is 0, and 0 minus 1 is -1. So -1, 1 squared minus 1 is 0, and what you can do is just solve these. And I guess we don't have room to include 4 either. Alright, so now this is our significantly puny little other table. So 0, -1. So it's kind of like a little dropout over here. So 0, -1. And well, what would happen when we get closer over here? Because remember, this part is still orange territory, but what about over here? -1 itself. So, well, it kind of drops off over there. And if we were to approach that, we could just plug it in. If we were to approach -1, we would get something around 0. So that means that we can put a little like open circle over here. So it's not orange stuff, but if orange was here, then -1, the point over here would be -1, 0. And orange is also significantly close to here, so be warned. -2, 1, 0, 2, 3, so eyeball it, and then 3, 8, and really that's all we can draw, unfortunately. And so that's a sort of good look on how our graph is going to look like. Now, what's the point of doing all this? Well, we're going to check for two things. Is there continuity? And is there a two-sided limit? Alright. So now, a two-sided limit would be a limit that's the same on both sides. But is that really the case here? Let's see. So, if we approach -1 from the left, so we'll use a negative sign for the left. If we're approaching -1 from the left, then that means that f of x will be 1. Another way we can write that is f of x is x approaches 0, as x approaches -1, the limit of f of x is x approaching -1 is 1. So that's what we can say. But that's from the left. So we have to put a tiny little cheeky minus right over here. See if you can spot them. Alright. So now, what about from the right, however? If we approach from the right, it looks like we get closer to 0 instead. So, two different answers. So that gives us x approaching -1 with a little cheeky positive sign. And that's 0. Since these two limits are unequal, there is no one limit that can unite them. So that means that we cannot have a two-sided limit because the one-sided limits are different. So you can tell if there is no two-sided limit at a point if there's a little drop. So if there's a little drop or a little rise, then we'll be sure that, there's that kind of disconnect means that there will be no two-sided limit. So you failed on the two-sided limit part. And is it continuous? Well, no, it is a typo because of the hole. So now let's talk about a different function. Let's say we had another function, and this time the writing is not going to be so complicated. F of x is 1 over x minus 2. Now, it still looks pretty hard, but I guess that's fine. Whoa. And the other way. And you pretty much know the deal by now. Why did I just write 0 on that step? And you pretty much know the deal by now. You just have to kind of be patient, people. You can speed this up if you want. 1, 2, 3, 4, 5. Maybe have a cup of tea. Write down some notes. Go back to the parts that you skipped mindlessly. And it'll probably take me a few years to finish this. -8, -9, -10. And -1, -2, -3, -4, -5, -6. And let's just look. -7, -8, -9, and -10. We don't have to do any highlighting because the entire thing is just one function. So 1 over x minus 2. So remember the two checks. Is it continuous? Continuous? And is it two-sided? Is there a two-sided limit? Well, let's see. If we have 1 over x minus 2, we'll need to make a table. Table of values. So, let's see. That should be enough. And xy. Now, 1 over 1 minus 2, that's going to be 1 over negative 1, which is negative 1. 1 over 2 minus 2, however, we'll come back to that later. 1 over 3 minus 2 is 1 over 1, which is 1. 1 over 4 minus 2 is 1 half. 1 over 5 minus 2, 1 third. 1 over 6 minus 2, 1 fourth. 1 over 7 minus 2 is 1 fifth. 1 over 8 minus 2 is 1 sixth. 1 over 9 minus 2 is 1 over 7. 1 over 10 minus 2 is 1 over 8. But what about here? That's so strange. Well, so we could also graph the negative parts, but I'm not very willing to do that. So goodbye. So if you've also noticed, there's no negative y values because there's a y asymptote y equals 0. So by 2. That was hours of work. That was minutes of work wasted. Alright. So now we have 1 negative, oh no. Anyway, I'm just going to keep this one over here. And we take 1 is negative 1. Oh, I forgot to say something about 0, which would be negative 1 half. And then you have 3, which is 1. You have 4, which is a half. You have 5, which is 1/3. 6, which is a quarter. 7, which is 1/5. 8, which is 1/6. 9, which is 1/7. And 10, which is 1/8. So now, you get this sort of strange function. And now we have minus 1, 1, 1/2, and so on. Let's just see if Desmos things were correct. Desmos. Alright, and we get, we have the function 1 over x minus 2. Yeah, that should be about good. Ooh. Turns out the equation actually looks somewhat like this. There's a vertical asymptote over here. So like it never touches x equals 2. So as you can see, it gets really close. But you can spot that it never manages to touch 2. It's kind of like Namibia and Botswana. Or Zimbabwe, I meant. Because their border looks something like this. But then there's Zimbabwe that blocks it off by one tiny bridge. So same kind of thing is going on here. Gets closer and closer but never manages to touch. And so, now, that means that there's nothing to find at 2. And while there is continuity, I mean, there is no defined limit when you get closer to 2. So there's technically no two-sided limit. However, this is continuous. Now, what we need to know is say, what if we had f of x is equal to x to the minus third? Well, we'll go back to decimals for that, and we just write x to the -3, and what does that give us? Another one of those kind of equations. Oh my goodness. So, there are some examples of equations that have two-sided limits but are not continuous. Like, for example, if I take a random equation, we could say this one, which has the same limit coming from the left and the right, but it's not continuous because there's a hole. And, of course, if we wanted something that's both continuous and has a two-sided limit, then we just take a regular graph. Alright?